Hi, let me begin by saying thank you for attending this talk. Now, this book, which I'm going to be talking about in this presentation, explores how art can be created exclusively from rectangles. It's also the first in a series of computer science textbooks that I'm writing targeting K-12 education. And I would also like to mention that how this book goes about teaching computer science is different from traditional curriculums, which are typically based either on Scratch or content provided by code.org. The book is freely available, so if you'd like a copy, send me an email and I'll send you a link. And currently I'm working on tying the contents of the book to educational standards. I'm developing lesson plans for teachers, and I'm also creating an online course that will prepare teachers to use this material in their classrooms. All right, so the first chapter of the book is about digital images. In particular, what makes up a digital image, how are they stored, and how are they displayed. So if you use the right software and zoom in on a digital image, you'll see that the image is made up of individual monocolored squares, and these squares are called pixels. So conceptually then, a digital image is a rectangular grid of pixels of various colors. Now these images can be stored in a variety of file formats, and two common file formats are PNG and JPEG. And on Windows, for example, if you hover over a file that contains a digital image, the system will tell you the dimensions, the pixel dimensions of the image, as well as the size of the file that's storing this digital image. Now, digital displays, you can think of them in a similar way. They are a rectangular grid of pixel display elements. So for example, a high definition digital display will have a resolution of 1920 by 1080 pixel display elements. Now the colors that make up a digital image, the pixel colors, can span a wide range. And the 24-bit RGB color model is the standard model that's used to describe these colors. It's an additive color model, and it's based on the primary colors red, green, and blue. Now symbolically, these colors can be described in a variety of notations, and the two most common notations are an integer-based description and a hex-based description. So the book provides a color picker that lets you familiarize yourself with the RGB color palette. And if you notice down here, you can see the symbolic representations. You can actually use the keyboard to enter values in here directly and see how that changes the color, the visual display. Now, at this time in the book, there's an assignment that gets you familiar with translating back and forth between these notations. And you use the color picker to do this. And the ability to do this is beneficial for assignments that follow later in the book. All right, so the second chapter in the book is about an art form that in modern times is called pixel art. Now, pixel art arose as a consequence of the technology that was used in the design of early video arcade games. And in particular, these game designs had to overcome enormous challenges both in hardware and in software. And so to give you some perspective of the difference in computational power that was available then versus now, right? What you see here is the Cray 1. It was the world's first supercomputer, and in its day was the fastest computer on Earth. This is the iPhone 5, which was released in 2012, and it is nearly 1,000 times more powerful than the Cray. Now, the gaming industry didn't have access to this kind of the Cray level computing power, right? It had to make do with much less. And just to give you some perspective, right, here's a digital image taken with a smartphone camera. Its dimensions are 3456 by 4608. And in the lower left corner, you see to scale the size of the display of the 1978 video arcade game Space Invaders. Now, Space Invaders is arguably the most influential video game in history. And the size of its display was 256 pixels by 224 pixels. And so what that meant was that all of the elements in the game, in particular here, for example, the aliens, you only had a handful of pixels to artistically express the idea, the visual idea of an alien. And it was under those restrictions, right, that pixel art as an art form came into being. Now, with that background, we're now ready to explore the creation of art on a digital canvas. And the first thing that we want to do is get comfortable with describing the positions of pixels on a grid. And so there's an interactive web app that comes with a book that gives you some practice with just describing the coordinates, the locations of cells on a grid. And so this one here, and it ties in with Lego, right? So this is kind of like it's a top-down view of a Lego base plate. It's interactive. If you got an answer, you can submit it. It will tell you whether you get it right or wrong. If you're stuck, it'll show you the solution. You can also turn on sort of the coordinates, the training wheels here, to see how these numbers and these numbers line up. Now, each of the apps in the book of this type has a corresponding test generator. And so the test generator for this app will generate 10 questions. Students can take the tests as many times as they like, but whatever they submit, the teacher will know how many questions they got correct, which questions they were asked, and how much time they spent answering each question. Now, at this point, sort of some math-related questions can be asked. And here's an example. There's many of these kinds of questions, but here's an example of one. On a 17 by 17 grid, what are the coordinates of the cell that is located at the center of the grid? Now, for a small grid, right, I can eyeball this. If the grid gets larger, I can maybe count it out, but there is a point if the grid gets large enough where I really do have to use math. So for example, if the grid is 529 by 529, it's really unrealistic to expect somebody to be able to count that out. All right, so there's another app that I'm not talking about in this presentation, and it basically gives, in effect, Lego build instructions in English. Place a Lego brick having this shape, this color at this location. And once they get comfortable with this English description of sort of these Lego build instructions, the next app, which is this one, translates those English sentences into code. So here's a put function call. It's called put2d. It takes 3 arguments: the dimensions of the Lego brick, the color, and the location. And this location right here, these coordinates are what I'm calling the reference point of the brick, and it is the pixel at the lower left corner of the rectangle. So what this function call creates is this rectangle right here. And you can play around with this. We look at sequences of function calls, and you get some sense of the artistic possibilities in this medium. Now from there, that chapter has focused on reading code, reading sequences of put function calls that were written by somebody else, presented by the app. In this next chapter, students take a more active role in constructing function calls themselves. And so this app here asks students to use mouse clicks to create function calls that create rectangles of various sizes and colors at various locations. So students are now paying attention to the structure of the function call, the order of the arguments. And let's see, what do we do next? So you get some practice doing this. And what we want to do next after that is look at constraining how many function calls it takes to create an artifact. So in this next app, you're limited. You only have 4 function calls that you're allowed to create this artifact. And so one thing that I haven't mentioned yet is that in the setting, there's such a thing as an empty brick. And an empty brick, an empty color, if you place an empty rectangle on the grid, it will erase whatever's underneath it. So the way to create this artifact with 4 function calls is to create the black and white portion first, and then to erase part of it. Now these kinds of optimization problems can become enormously complicated, and the goal of this app is not to make it that hard, but there are some hard problems in here, and it's not always involving the empty color where you're erasing stuff. But there is layering happening here. So you do have to decompose artifacts subject to a certain set of constraints. So at this time, right, there's some interesting assignments you can give is have students design their own optimization artifact. And again, these can be very complex. So there's a wide range of possibilities here. And a follow-on question then is, if a student has created a really cool artifact that's kind of it's difficult to see how you could construct it in 10 function calls, let's say, how do they know that somebody else can't come along in the future and say, hey, I can do it in 9? So that is a very deep question in computer science, this type of question. And I wouldn't expect students to be able to comprehensively answer it at this point, but it is good to have them think about this kind of stuff. Now, when you're constructing pixel art, if the pixel art is simple enough, you tend to pursue this sort of optimization-based construction, the fewest number of function calls, get it built as quickly as possible. However, if pixel art gets more complicated, there's a point where that doesn't work. That becomes too much complexity. It gets introduced as a result of doing that, and you start making mistakes, the human who's doing this, right? And so to overcome that or to deal with that kind of complexity, you have to be very disciplined about how you go about creating pixel art. And one algorithm that helps with this is a row major construction algorithm. And so this algorithm here says, if the pixel art is complex enough, or if you decide to apply this algorithm, you construct pixel art one row at a time from bottom to top, and in each row you construct the pixels from left to right. So there's an app that makes sure you understand how this algorithm works. And so for example, row major would be, I start from the bottom, I do this row first and that row. But let's say I somehow got this wrong, right? I didn't quite understand that I had to do this. So if I start with this, I'm starting on the left side, I'm thinking that's good enough. And then later I come back and I try to do this, the app will tell me that you didn't do this. You didn't do it right. And so basically, if you can solve these exercises, you do understand how to apply this algorithm. All right. So with a fairly comfortable understanding of the elements of put function calls and reasoning about how to sequence them, we take one more step towards coding, and this is a block-based coding environment. Again, we're trying to avoid typing. And in this environment, you now have to pay attention to the entire structure of a program. So the graphics library that you're using, the Lego base plate, if you will, that you're creating, the size of it. You have some put function calls here. And at the end of this put function call sequence, you actually have to display, explicitly display the artifact. And so most of this construction doesn't involve any keyboard input. However, there are 4 places where there is keyboard input. And this opens up the door to typos, right? Syntax errors. And BLite is pretty good about recovering from those. However, there are still other kinds of errors that you could create that are not necessarily syntax errors directly, but they are things that don't make sense. So for example, if I scooted this rectangle too far to the right, I would reach a point where it goes off the grid, which doesn't make any sense. Now the tool tells you this. If I forget a semicolon, it will tell you this too. And then also each of these program blocks has a help option that takes you to a YouTube video, a short YouTube video that explains what the block does and how to use it in a program. So with that understanding, right, an assignment in the book involves creating a very small artifact that just consists of 4 of these squares of different colors, possibly. That doesn't have to be 4 colored squares. And if you notice here on these 2 examples, the squares are the same, the dimensions of the digital image is the same, but their file size is different. And that has to do with how JPEG compresses digital images. And so an example here is find, in a 2x2 artifact, find the color combination that leads to the smallest file or perhaps the largest file. So in that way, students get to explore and get at least some informal understanding of the relationship between JPEG compression and color. All right, so that gets us to the next chapter, where we build pixel art in earnest. And here's an example of a butterfly that I created in B-Light, and I used a row major algorithm to construct this butterfly. However, on the other end of the spectrum, of the complexity spectrum, here's a very simple artifact. So this is an alien blob that I'm calling Blink. And using a row major algorithm is perhaps overkill to construct this thing. So in this case, you can explore some kind of optimization where the fewest number of function calls. And so here's an algorithm that says, I'd like you to do a greedy algorithm based on the heuristic that you try to place the largest rectangle first. So color in as much of the body as possible and keep doing that with whatever is remaining, and then build the eye on top of it. Now, if you use that heuristic, you'll get this kind of a decomposition of this alien blob. However, there are other heuristics that you can use. And this one here concerned itself, you try to place the widest rectangle first. And that gives you a different composition. And this composition, this approach gets you a shorter program. And then there's another heuristic that the book looks at that gets you an even shorter one. And so an assignment for the students at this time, right, is to go online, get a pixel art image of one of the Pac-Man ghosts, and decide which heuristic you want to use to construct this thing and code it up. All right, so the next chapter in the book is about neoplasticism, which is an art theory that constrains how you should go about creating art. And in particular, neoplasticism, you do not seek to create the illusion of three-dimensional space on a two-dimensional canvas. Now, when you're painting, there's sort of two techniques that artists use to create this illusion of three-dimensional space. One of them is perspective, where differences in size give the impression of depth, and the other one is shading, where differences in color capture how light would reflect off an object that is not flat. Now, in addition to that, neoplasticism limits the elements you can use to create art to just a handful of things. You can create horizontal and vertical lines. You can use the primary colors red, yellow, and blue, as well as the non-colors white, black, and gray. And so Piet Mondrian, who defined neoplasticism, believed that by limiting how you go about creating art to these elements, you could create a universal visual language that would be accessible to all people, regardless of their cultural backgrounds. Now, here are paintings by the two most famous artists in this style. And in particular, Piet Mondrian is considered one of the greatest artists of the 20th century. And to give you some perspective, this painting right here sold in 2015 for over $50 million. And both of these artists are highly regarded in modern times. Now, what Piet Mondrian's signature paintings do, right, is they partition the canvas. And so that lets you take a look at this from a mathematical perspective. So you can create problems that, you get this many horizontal lines, how many rectangles result in the partition, vertical and horizontal lines. You can do stuff like this. And you can even write Bricklayer programs, B-Light programs, where you are given some number of vertical and horizontal lines and line segments. So a line segment here is a line that wouldn't go all the way across the canvas. And the goal then is to create a partition so that no two rectangles have the same dimensions or the same area. I mean, you can have different criteria here. Here's an example of an abstraction of a Mondrian-style painting, and it is accompanied by an algorithm that tells you how to color in the rest of the canvas. And the algorithm is underspecified, and what that leads to is that you can actually have different solutions. The solution is not unique. Now, engineers will tell you that this is actually a good thing, that if you have wiggle room in a design, this is where the engineering magic takes place. All right. The next chapter is about an art style or art movement that emerged in Southern California in the late 50s, and it's called California Hard Edge, or simply Hard Edge. And it's different from neoplasticism in a couple of important ways. First of all, you have the full color palette available. You can have a bold use of colors, and you're not partitioning the canvas anymore. And so this notion of overlapping rectangles is a reoccurring theme in California Hard Edge. Now, the reason why it's called Hard Edge is because when artists paint, they can use soft edges, disappearing edges, and hard edges to focus your attention on the painting. And the human eye tends to be drawn towards the hard edges in an image, where your peripheral vision in some sense is the blurry edges. So here are two paintings in this genre, and all of the artists in the book, right, there's an assignment that says do a tribute in the style of such and such, and these assignments are accompanied by links to online galleries where you can familiarize yourself with the work of these artists. And notice California Hard Edge is not just about rectangles, but it is an important part of this style. So with the idea of overlapping rectangles, right, you can create artifacts like this. Of course, you could think of these corner pieces as rather being constructed as by two put function calls, a horizontal one and a vertical one. But first of all, that would lead to a longer program. And second of all, the abstraction of thinking about it in terms of overlapping rectangles influences your decomposition of this kind of an artifact in your mind, right? So here's an example of a problem where you're supposed to use only squares of different sizes to create this artifact. Now, the chapter that comes after that is not really an official art form. It's just something that I thought would be a nice next step in sort of this progression. And the idea here is that not only can you have overlapping rectangles, but the rectangles are transparent. So that opens up the door to mixing of colors. You can, of course, add this vertical and horizontal stuff, but you don't have to. But you have to be able to mix colors, right? And that then lets us explore, like, how do we go about mixing colors? And in our RGB color model, we can do this mathematically. So there can be formulas. Again, we can use the color picker to plug in some colors here, apply this formula, mix the colors, see if we like the results. And what we're using as a point of reference here is paint color mixing models. So the two well-known ones are RYB and CMYK, and these are subtractive color models for mixing paints. And so every color that you can think of somewhere falls on this wheel. And one thing that you may not do in this color model is mix all three primary colors, because then you'll get something approaching black. Now, here's an example of an assignment in this chapter. So you get to pick three colors, any three colors you like. You have to build these wireframe squares that have a certain thickness, where the wireframe has a certain thickness, and they have to overlap in a Venn diagram-like way, and you have to mix colors accordingly. So here's an example of a solution to that assignment. And then the last chapter of the book is about generative art, right? So DALL-E, Midjourney, Night Cafe, that kind of thing. Here is the B-Light butterfly that I'd coded. Now these tools, these art generators, originally you had to type in a text prompt and it would generate an image, but nowadays they're more capable, and you can drag in an image yourself and have it generate something based on that image. So it treats the input image as a text prompt in some sense. So here I depixelated my butterfly. I also said, what would it look like if Van Gogh was painting this? And these art generators, because they are trained from images drawn from the internet, it introduces the possibility of bias, right? This is social impacts of computing. And so here are some images of professionals that I generated. So who is the CEO? Who is the English teacher? Who's the computer programmer? Right? So now we're having bias in perpetuating biases. And then beyond that, right, you also can have threats to the art industry in general, right? And so I used ChatGPT, which is a sister technology to DALL-E, to have a conversation with it about the social impacts of these kind of tools, right? And so I had to argue for and against the idea that art generators are a threat to artists. And then I took those answers, its answers were basically humans are original, DALL-E is just based on stuff that it's seen. But that doesn't entirely ring true because, for example, Voltaire said, look, we're not really original at all. We just kind of incrementally build on what came before. And so if you ask it those kinds of questions, right, you can ask it follow-on questions and it will respond, right? It knows what you had talked about earlier. And you can say, so how is what DALL-E does different from what humans do? And it goes back to this environmental influences and stuff like this. And then you can get to another question where you say like, hey, what happens as the metaverse and the physical world merge or become closer, connected in a closer way? What happens then, right? Are these differences that important? And then sort of a last sort of open-ended question is, how well does what you see on the internet reflect humanity? Because history books tend to be written by the winners, right? So they have sort of a whitewashed version of what really happened. And the internet maybe has the potential of being more raw than that. All right, thank you. That's it.